looking at set A, right? They told us in the beginning that all of these data sets had the same mean. So if I'm looking at the mean here, that's the mean, right? That's either mu or x bar, right? That image right there is representing the mean. Remember, the mean would be, in this case, it's the middle, right? The mean is going to be the middle, especially since it's symmetric. We also know, just based on the bars of our histogram, that if I'm looking at the middle, which is contained, if I'm looking at that tall bar in the middle, it's going to have the most data, right? Compared to the other bars that are out here at the ends, right? Those are short bars, they have less data. So in terms of standard deviation, this particular histogram right here would probably have a smallish type of standard deviation because the majority of my data is occurring in the middle. Remember, standard deviation is how spread my data out, how spread out my data is. So when I have a tall bar right there, and the tall bar happens to contain the mean, the average, standard deviation is how far away from the average I am. Well, I'm not very far, or am I? Because I'm right there at the middle. Does that make sense? Yeah, for some of you I hadn't come around and talked to, does that make sense? Okay. So if we look at this next one here, we said that that was also symmetric, but it's a uniform distribution. There is no one particular bar that has the most data in it. All of them have the same amount of data in them, don't they? And if the standard deviation is talking about how far, how spread out my data is, then I would say I've got equal amounts of data as I move farther away from the center. Now, if we're comparing A to B, set A to set B, and I want to know who has the largest standard deviation, whose data is spread out the most, A or B? B. B has the most data spread out compared to A, doesn't it? Or conversely, I don't remember how it was asking who had the smallest. A would have the smallest, B would have the largest if you're comparing the two together. Now, if we look at C and D right there, right, those are both skewed left, they're both skewed. Both C and D are skewed, all right? And we were told again that about 2.5 is where the mean is. So we're somewhere here in the middle of each of these graphs, right? But if we're talking about the distance away from the middle, we have the same amount of data, it almost appears, moving all the way out there, right? Compared to this one over here, correct? So both of them have, they're almost symmetric to each other in a way, right? They both have data that's occurring out to the sides. They both have roughly the same amount of data within a bar and a half to the mean, right? Okay, so we would say that those standard deviations would have to be the same. And then compared to the last one, what was the type of what was our description for the last one? Bimodal, that's right. So here I have the middle, right? That would be the middle of my distribution. And I've got, it's symmetric. And we also know that those two bars at the end, right? My bars are increasing as I get farther away from the center, meaning that I have more data farther away from the middle, correct? If I have more data outside at the edges compared to a little bit in the middle, then that would imply I have a larger spread, right? I have more data out on the edges. Okay, so if we were to try to identify the data sets or the standard deviations up there, well, because we know C and D are both the same, we would say that their standard deviation was at 1.026. Okay, so they're the same. You can count those off. We know that this data set A is actually the one that has the largest peak in the middle. It has the majority of its data right in the middle, which means that it has a very small spread compared to the rest of the data sets you're looking at. So it would imply that it is the smallest standard deviation, or 1.124.
And that's because most of the data is in the middle.
Most of the data is in the middle, so the smaller the standard deviation is, the closer it is to zero, okay, then that means you have no spread, right? And then the largest spread actually occurs down here with data set E, so the standard deviation is 1.589. And by process of elimination, then you can come back and say that 1.451 has to be our uniform distribution. Okay, so it kind of gets you thinking about standard deviation, right? It's a little bit different. I'm not just simply asking you to punch a button or calculate the standard deviation. I'm asking you to understand it, right? Okay, and it's a little bit more than what we're used to seeing for some of our stuff. All right, are there questions or comments on that particular activity? No? All right. Now, we said Tuesday of last week, or Wednesday of last week, that's what we talked. What did we call this rule right here? The empirical rule. I would definitely make sure you had that written down on something. That's for sure. The empirical rule says that I can talk about any particular data set that has what type of a distribution? Normal distribution. All right, so if I have data that is from a normal distribution, then we know certain characteristics about the data. That I can say 68% of all my data is going to fall within one standard deviation above or below. 95% falls within two standard deviations, right? And then I can keep going. Okay, so that's what we were talking about on whenever. Last we were together, Wednesday of last week. And today what we're going to talk about, so we're going to talk about 3.4 and we'll cover 3.5 on Wednesday. All right, we'll cover 3.5 on Wednesday, and then you have a test over chapters 1 through 3 on Monday of next week. All right, okay. So 3.4 is talking about a little bit more specifically. We're going to talk about z-scores, and then we'll talk about quartiles. Now, z-scores is just a way for us to talk about the number of standard deviations away from the mean. Specifically, the number of standard deviations that we are away from the mean. Now, we would say that, and I'll explain these to you in just a minute, so just make sure you get this written down for your own knowledge right here. Z-scores are unitless. I'll explain that in just a minute. We can find them by just converting them to some sort of standardized scale. That's how they are found. And what it does is it allows us to compare apples to oranges. And the best way for us to explain that, so I would just make sure you write down the very first part, that they are the number of standard deviations the data is away from the mean. They are a value. They are the number of standard deviations that we are away from the mean. And I'm going to add to this in a second. How many of y'all took the SAT or the PSAT, something like that in high school or to get into college? All right, so you took the SAT, or maybe you know some people who took the SAT, and you had scores ranging between the maximum score you could make was like 1,600, right? Right, so it's 800 was the score for math and 800 for English. How many of y'all took the ACT? Anybody take the ACT also? What was it based out of? 32 or something like that, right? It's some number. It's not 800. Okay, that's the point of that. It's not 800. Now, universities and colleges typically require that you take that test to enter into the college, right? Enter into their university. And let's say that you work in admission and you have one student who took the SAT, but you had another student who took the ACT. And you only have so many slots, and so you're going to admit the person who had the higher score. Well, how do I know
who had the higher score if they're both based on different scales. If the SAT is based out of, let's call it 1600, and you made 1200 out of 1600, and you have somebody else who took the ACT, which is gonna say, I'm gonna say it's based on 32, and you had somebody who made 30 out of 32. Who made the better score? You don't know, do you? Because you're comparing apples to oranges in that manner, all right? It's like if I wanted to compare inches to centimeters, right? They are not the same. So if I am thinking about that, so here is our normal distribution that you saw a minute ago, right, with our empirical rule. And what we know is that testing scores are normally distributed. So if they are normally distributed, then I can take that data and I can figure out where does SAT person fall in that data set compared to ACT person in that data set. And the way that we do that is we have to convert them into a common standard. That's what our Z-score does. Okay, oh, that's the wrong screen. So what we're looking at here, and I'll explain this again in just a minute, but here you have the line that represents the SAT score starting all the way from 0 or 200 to 800. Does everybody see that line that says that? Right below that are the ACT values. Apparently it goes up to 40. We've got 5 all the way up to 40, right? Those are the values if you're thinking about that empirical rule, okay? And what we've done here is I can say, okay, if I were to standardize this out and I say the middle of my graph on a normal distribution is now going to represent 0. So the mean is going to be 0. And as I move above the mean, I have a Z-score of 1 standard deviation and 2 standard deviations and 3 standard deviations, just like we saw before. Or I can go below and I can call it 1 standard deviation. -1 would be below, -2 would be below the middle, -3 would be below the middle. And in essence, what we're doing is we are multiplying the Z-score times the standard deviation of my data set to come up with a value that we can talk about. So I'm going to move down here. This is what I want to make sure that you put on your notes paper right there. And what we're saying is we can only use our Z-scores on a normal distribution. So the data type has to be a normal distribution. And the formulas, we have 2 formulas, just depending upon if you're talking about a population or a sample, but they're the same. So we have the Z-score represented by my data point, which is X, that's always our individual data point, minus mu divided by sigma. All right, so it's my data point minus the mean divided by the standard deviation. That's both of those formulas say exactly the same thing, right? The second formula over here says my data point X minus the mean of the data set divided by the standard deviation of the data set. This Z-score over here says the data point minus the mean of my data set divided by, or the mean of my population divided by the standard deviation of my population. They're the same things, all right? That's how we calculate the Z-score. And all the Z-score does, if you want to keep telling you this, is it tells me how many standard deviations above or below the mean I am. And then I can compare apples to apples and apples to apples, right? I can compare the 2 groups together. If I knew how many standard deviations my SAT person was versus my ACT person, how many standard deviations I am above the Z-score, right, their mean, then I can compare them. Okay. So let's put that into practice. Now, I do want to just highlight a few things here before I forget. When we are thinking about the standardized, when we think about a z-score, again, you have to use the z-score on a normal distribution. Just look at the variables in our formula. We can only apply mean and standard deviation to normal distributions. And technically what we're doing is we are zeroing out the middle. So that now becomes 0. And then we are adding above it, or we are talking about below it. So we're going to work an example, and I gave you this example on your paper there. So you have a copy of it as well. Birth weights, okay? So we're going to look at this one and we're going to talk about birth weights. In 2010, babies born after a gestation period of 32 to 33 weeks had a mean weight of 2,300 grams and a standard deviation of 715. In the same year, babies born after a gestation period of 41 weeks had a mean weight of 3,520 grams and a standard deviation of 480 grams. So suppose that you have a 33-week baby who weighed 3,000 grams and a 41-week baby who weighed 3,900 grams. We want to know which baby weighed less relative to their gestation period. So in what we're talking about are preemie babies versus full-term babies in essence, right? Okay. So since you have this on your paper, my suggestion would be either to underline, circle, something like that. I always think about doing that when I have something to write on. So I've got my preemie babies who have a mean weight of 2,300 and a standard deviation of 715. So let's write that down. So I have a mean of 2,300 grams. I've got a standard deviation of 715. Okay, and then I've got my full term who have a mean weight of 3,520 and a standard deviation of 480. So I have full term 3,520 and a standard deviation of 480 grams. So the question is, suppose you have a preemie who weighed 3,000 grams. Okay, so the preemie's over here. That is what X is. That's my, so X, just X by itself is going to be usually my data point. That was the preemie baby. And that baby weighed 3,000 grams. And then reading on, we have our full-term baby who weighed 3,900 grams. So that X is 3,900. Okay, so we want to calculate the z-score for both of these babies. All right, 3,900 grams. So I'm going to come over here and I have my z-score for the preemies. Now remember, the formula says I'm going to take my data point, which is the weight of the individual baby, 3,000, minus the mean for that category of 2,300, divided by the standard deviation of that category. And we want to go to 2 decimal places. So when I do this in the calculator, remember order of operations, say I'm going to subtract the numerator and then divide that by the denominator. So everybody should end up with 0.98. Can everybody make sure they get that on their calculators? Okay, 0.98. Now let's do the same thing for the full-term babies. And I'll explain what this score is in just a second. We can't really compare it. I don't have anything to compare it to yet. We do the same thing over here. We know the full-term baby weighed 3,900 grams. The average for the 30 terms, or the mean for the 41 weeks is 3,520. And the standard deviation for that category is 480. And when I divide that, I end up with 0.79, right? 0.79. Okay, so if we're thinking about this, the middle is at 0, right? When I'm comparing, who's farther away from the middle? Right? 0.98 is here, and 0.79 is there. So, who weighed, what are we asking? Which baby weighed less relative to their gestation period? In other words, who's closest to the middle? Oh, full-term baby, right?
Yeah.
Because that's the Z-score. Relative to other full-term babies, that's what that means. Relative to other full-term babies, that baby weighed less. The preemie baby, relative to other preemie babies, weighed more. Okay? That's what Z-scores allow us to do, is we are able to compare things that are not the same. You have preemie babies who have their own set of mean and standard deviations, and you've got full-term babies who were their own set of means and standard deviations. All right? And so in this particular case, I'm looking at, okay, if this is 0, right? 0 is 0 is 0. And so if I want to know who weighed less compared to that of the two values, who's closer to 0, right? Okay. That's what a standard deviation, that's what a Z-score allows us to do. Now, what I want you to do is, I have the other one on your paper, and I'm trying to trick you on this one. Okay, so I'm just telling you right now, it's not going to be what you think. We've got a triathlon problem right there, right? You have two runners. You have Roberto and where is the other one? And Zandra. Roberto and Zandra. So in marathon running, right, you have an average time and standard deviation for the men, and you would have an average time and a standard deviation for the women. So we have our two categories. I want you to compare and figure out who ran the better race compared to their gender. Who ran the better race? Think about it, what it means also to run the better race. Once you think you've got an answer, see if anybody around you can agree.
Remember, subtraction is not commutative, right? Order matters in this particular case. All right, were you able to calculate a z-score for Roberto at -0.7 and a z-score for Zandra at -0.73? Who ran the better race?
She did.
Zandra did, right? Zandra ran the better race, didn't she? She ran it faster, didn't she? Relative to the other men that were running. All right? That one's kind of tricky, right? You gotta think about it. She had to run faster. So she would actually be farther away from zero, wouldn't she? Less, you're thinking in that direction. Kind of a backwards one. Okay. All right, so Zandra did. All right, the next question that it's not on your paper, but I've added it because you have a problem like this in your homework and we need to talk about how you could go about possibly finding this. Did anybody have a question on calculating the z-score for Zandra or Roberto? No?
Okay, if it's a negative.
It was supposed to be a negative, yes. Yes, and that's a good question because remember that on z-scores is when we are gonna have negative values versus positive values because it's technically talking about, it's telling me how far I am away from the mean and in what direction. So in this particular case, Roberto was 0.7 standard deviations below the mean. Right, that's what the negative sign is implied. Now, the last one that we're gonna have time for is this question right here, all right? So this question is asking us, it says here that suppose you score 600 on the math portion of the SAT, but you wanna know what that equivalent score is on the ACT. Right, there's that kind of testing that I was referring to. All right, so you score as 600 on the SAT and you want to know what is that equivalent score on the ACT because the college you're applying for, they only take ACTs for whatever reason. Now, in order to figure out what that equivalent ACT value is, first, I have to figure out what the z-score is. How many standard deviations is my SAT score away from the middle? Right, that's what I want to find. How many standard deviations away from the middle is my SAT score? So to do that, we're going to calculate the z-score. All right? For when it was 600. So the z-score is my value of 600, right? I scored, that's my data point, 600. Minus the mean of SATs, which would be 514, divided by the standard deviation of SATs, which is 118, right? That's the same thing we did before. It's the X minus the mean divided by the standard deviation. And to two decimal places, I think we all know how to do this one, so I'm going to move on. I find that my score of 600 is 0.73. So for my score, I'm 0.73 standard deviations above the mean. Okay, so I found out that my score is 7.73 standard deviations above the mean. So I want to convert that. What would I have to score then on an ACT? Well, the ACT, it's gonna be some value, right? It's gonna be some value for the ACT, but it's gotta be 0.73 standard deviations above the mean, doesn't it? So to find my ACT score, okay, I am going to take the mean, which was 21.1 for the ACT, plus, because I'm gonna add to that, right? I'm gonna say the mean is the middle, and don't forget, my SAT was 0.73 standard deviations away from the middle. So I'm gonna take the middle for the ACT, and I'm going to multiply the standard deviation of 5.3, that's the standard deviation for the ACT scores, times the 0.73 that I calculated. That would be, I don't think I have the right number on here. Somebody do that math for me in their calculator really fast. 5.3 times 0.73 and add that to 21.1.
2.87?
24 what?
24.9.
24.96?
7.
24.97. Okay, so remember, standard Z-scores tell me how many standard deviations away from the middle I am, right? What we found was that my SAT score was equivalent to 0.73 standard deviations away from the middle. How much is that in terms of ACT? So I take how far away from the middle I am at 0.73, I multiply it times the ACT standard deviation and add it to the ACT middle. All right? That's how we can go from one into the other. Okay? So I have to have that, it's a scale. It's a scale. So you know how if you see you know how when we scale up, let's say Hot Wheels cars, right? They're scaled up by some sort of value, right? That's what our Z-score does. It scales my standard deviation up by a certain number, higher or lower than our mean. That's all a Z-score is. It's a standardizing of it. All right, so we got most of the way through here. We didn't need to talk about the last part of this, which will be quartiles. And so when we come back, we'll finish up with quartiles, but we'll also talk about 3.5, which is box plots. And those kind of go together anyway. Please be sure that you're reading this information and that you can take that second quiz or take the second attempt on that quiz